In this video, we're going to talk about polarizability. So polarizability is often mentioned in organic chemistry as one factor in comparing nucleophilicity of molecules, but its definition is often glossed over, and this video aims to provide a more formal understanding of polarizability. As a reminder, polarizability is a measure of how easily a molecule's electron cloud distorts. So polarizability, a measure of how easily a molecule's electron cloud distorts. Now, before we jump into the more concrete definitions, let's first talk about why polarizability is important. So why is polarizability important? Well, a molecule's polarizability partially determines how it interacts with other molecules, and these intermolecular interactions are very important when considering how a molecule acting as a ligand will bind to a substrate, which has implications for drug design. Polarizability affects intermolecular interactions. Which affects ligand substrate binding. Which influences drug design. Next, polarizability is also correlated with the electronic structure of a molecule, and it can be used in QSPR or QSAR models. These QSPR, QSAR models are then used to predict other properties or interactions of a molecule. Okay. So, for anyone who is unaware, QSPR stands for quantitative structure activity relationship, and QSPR is structure property relationship. And what these models do is they take in various properties of a molecule and attempt to predict other properties of that molecule. And polarizability, again, is useful in these models because it is correlated with electronic structure. Okay, so now that we've talked about why polarizability is important, let's define polarizability. Polarizability. As we mentioned before, polarizability is a measure of how a molecule's electron cloud is distorted. But more formally, it is how a molecule's electron cloud is distorted in the presence of an external electric field. And this is important because then it gives us a way to start quantifying the polarizability. So if you have a molecule, any molecule, let's say water, and you place it in an electric field, that molecule, the water, will eventually have an induced dipole pointing in some direction, often in the same direction as the electric field. And this induced dipole is called mu star. And so, to measure the distortion of the molecule's electric field, or the molecule's electron cloud, we relate these two values by saying mu star is proportional to the strength of the electric field. And note that we are saying that the polarizability, that the induced dipole points in the same direction as the electric field. This is not always true, in which case we have to use a polarizability tensor for the value of alpha, but we won't talk about that in this video. So, note that here water would already have a permanent dipole embedded in it, but what the electric field will do is the electric field will induce a dipole in water as well. And the induced dipole will be the sum of the effect of the electric field itself, as well as the permanent dipole. So in other words, the permanent dipole has an effect on the value of alpha. So what is alpha? So this proportionality constant here, we have alpha. This is the polarizability. And so this makes sense because the greater the polarizability, that means the greater the induced dipole will be in the presence of an equivalent electric field. So based on this equation, we can think about the units of polarizability. So the electric field has units of volts per meter, while an induced dipole has units of coulomb meters. And in order to get these two units to equal, alpha, or polarizability, must have units of volts. Let's see. Volts goes on the bottom, meters squared on top, and coulombs on top. Alpha will have units of coulomb meter squared over voltage. And so this unit, even though it's correct, is slightly unwieldy. So we have a way to make it easier to use. And we divide alpha by a constant. So alpha divided by a constant, which is 4 pi epsilon naught, is equal to what we call alpha prime, or the polarizability volume. So why is it called polarizability volume? Well, 4 pi doesn't have units, but epsilon naught, the permittivity of free space, has units of coulombs per voltmeter, which means that if we divide the polarizability alpha by epsilon naught, then we get that alpha prime has units of coulomb meters squared over volts over coulombs over voltmeters
the coulombs and the volts cancel, and then meters goes on top, which means the units of alpha prime is volume, and so that's why it's called polarizability volume. So now that we know the concepts, you'll actually see that in most tables, or when you're looking up the polarizability of a molecule, you'll see that it's given as the polarizability volume alpha prime. So that's enough of the theory of polarizability. How do we actually go about using this, or how do I find information about this? So how do we actually go and find the polarizabilities of different molecules? Well, I found two tables that are quite useful. So the first is this table of polarizabilities, which lists the polarizability estimates for every element in the periodic table. And this can be used to compare polarizabilities between larger elements and smaller elements. There's another database of polarizabilities from NIST, the National Institute of Standards and Technology, and they list a lot of molecules and their alpha values, or the polarizability, in angstroms cubed, which is a common unit used for polarizability. And here we see a lot of commonly seen molecules in organic chemistry, like formic acid or chloroform, etc., ethylene, etc. And so this table is very useful when you're comparing the polarizabilities of molecules. And finally, for molecules made up of second row elements as well as hydrogen, or elements below the second row or below, there is a good proxy for determining the relative polarizability of that molecule. And that proxy is the number of valence electrons, or NVE. And this kind of makes sense because the more valence electrons you have, and those valence electrons are the ones furthest away from the nucleus and most likely to be distorted. So the more you have of those, the higher your polarizability is. And the reason why this doesn't work for elements above the second row, or the reason why it doesn't work if your molecule consists mostly of elements above the second row, is because the higher row elements contain d orbitals and f orbitals, which also affect how the electron cloud distorts. And so the metric isn't or this proxy isn't the most correlated anymore. So, for example, when we can use this, we can compare, let's say, methanol or CH3OH with propanol. Which is C3H7OH. And here we see that methanol, the number of valence electrons, equals 4 from carbon, plus 4 from the 4 hydrogens, plus 6 from oxygen, which is 14. And propanol has 4 times 3 plus 7 times 1 plus 8 times 1, actually. 8 times 1 plus 6, which equals 26. And propanol almost has double the number of valence electrons as methanol. And because these molecules consist mostly of second row elements, and in fact they are entirely second row or below elements, if we compare their actual polarizabilities based on this table from NIST, we see that propanol has an alpha prime of 6.67, and methanol has an alpha prime of 3.210. And we can see that as the number of valence electrons almost doubles, so does the polarizability.